I welcome Pallavi to give a lecture on chemosensors for iron and iron detection, the versatile role of iron.
A very good afternoon to all of you. Myself Pallavi. So today I am going to deliver a lecture on chemosensors for ferrous and ferric detection, the versatile role of iron. So moving ahead, I would like to ask, can you guys or anyone think that can you live your life without metals? Anyone, if he or she is thinking that yes, they can stay without metals, anyone out of you can stay without metals? Yes or no? Yes, very good. Nobody can stay without metals. So one of them is iron. What is iron? Iron resembles the symbol of Fe. So with atomic आ रही है आवाज ये ठीक है फिर okay. So it's a transition metal, or we can say that it belongs to a group of elements which can show a various oxidation states and can form a coordination complexes. It is lustrous silvery grey metal and that plays a critical role in both Earth's geology and biology. As we see around ourselves that the phones, mobiles, infrastructure, buildings, everything around us is basically made up of metals, and iron play crucial role among these all. As iron is widely used in construction, manufacturing and as an essential element in biological system, such as if we talk about hemoglobin, iron is present in the ferrous form in our blood. So moving ahead, this is the basic chemistry of iron. Here having atomic number of 26 with 55.8 atomic weight and high melting and boiling point, which makes it more ductile, or we can say that it has a more strength, so it can be used for the formation of bridges, buildings, etc. So now, okay, fine, we are having a iron, it is already inbuilt in our body. So from where we get in the nature? It is also present in nature. How will extract it from the nature? It is present in the natural mineral resources known as ores, from where we get iron. These are the four main ores of iron, basically hematite, magnetite, siderite and iron pyrite. Out of all four, two are very main, that is hematite and magnetite. They have a high abundance of iron in them. So moving ahead, moving to the chemical properties and history of iron. It has chemical properties, oxidation state, activity, etc., etc. Firstly, we are going to discuss about oxidation states. Iron is present in +1, +2 and rarely in oxidation state of 0, that is pure metal, and is present in +4, +6, and some of these two are the main complexes which basically present in +4 and +6. So we'll discuss one by one. So iron in a zero oxidation state. So iron is rarely present in zero oxidation state as compared to +2 and +3, that is ferrous and ferric. It is the examples of that are, this is basically found in metallic iron, or we can say that as a free iron as a form of nails, constructions, tools, industries having the oxidation number 0. Further example is FeCO5. Here it is a metallic compound with carbonyl is having a neutral, so therefore the charge is going to be 0. So here it is, iron is in a zero oxidation state. Now third example is ferrocene. Basically it's a ferrocene analog. Basically ferrocene is in +2 oxidation state because there we have a pentene rings up and down side. But here we are talking about benzene rings, so therefore its benzene have no charge, so therefore it's a neutral and it can act as a sandwich compound. Here we can say that iron exists in a zero oxidation state. Now what happens if I remove the 2 electrons from iron? It will exist in a +2. The configuration will come out to be argon 3d6, and due to pair of 4 unpaired electrons, it is paramagnetic in nature. So, have you ever thought of that how iron hold inside the water molecules, how iron stay inside the water molecules? This was explained by VBT, that how bonding take place. VBT considers the open hybrid orbitals of metal with the lone pair of ligands. Now, what happens if I talk about VBT? It occurs in it has two options, outer d orbitals or inner d orbitals. Outer d orbitals, if I take the example of FeH2O6, 2 positive, here central metal ion is having a 2 positive charge because H2 is a weak ligand and with a no charge, so iron in a +2 oxidation charge. So what will be the hybridization? Here, if you look at the image, if I talk about Fe2 positive, it is 3d6, that is 4 unpaired electrons. And now so what happen is that now H2 will donate its electron to the sp and d orbitals of iron. So leads to the formation of sp3d2 and the geometry will comes out to be octahedral. If now here ligand is weak field ligand, so therefore no pairing will take place. There are two type of ligands, weak field ligand and strong field ligand. Weak field ligand will do the less splitting, therefore no pairing will take place. In strong field ligand there is a large splitting and therefore pairing will take place. Now if I talk about higher inner d orbitals, here the example is FeCN6 4 negative. It is in the form of ferrous. Now the electrons will get paired because of the presence of Cn bond, because Cn is highly strong. So it will use the inner d orbitals of 3d, 4s and 4p. So leads to the formation of d2sp3 and geometry again remains the same, that is octahedral in nature. These are the two examples, they both are in octahedral geometry. So this is a tetrahedral geometry where Cl is act as a weak field ligand. Weak field means no pairing. Hybridization will come out to be sp3. Now what is ferric ion? If I remove the 3 electrons from the iron, it leads to the formation of ferric and the unpaired electron will comes out to be 5. This is the example in another, here is the example. If I take about this FeCN6 whole thrice, FeCN6 3 negative, it will lead to the formation of pairing and leads to the formation of D2sp3 hybridization. If in the same case, if I'll take this ferrous, it will also lead to the formation of D2sp3. The difference is that in ferrous, it is diamagnetic, and in ferric, it is paramagnetic due to presence of unpaired electron. Now, firstly, I had discussed about the oxidation state, that was very basic as we had studied in the junior classes. Now I talk about the reactivity. When we were kids, we used to see that we purchase iron or nails, we used to see that there is rusting of irons. What happens? When iron interact with the water in the presence of oxygen leads to formation of iron hydroxide, which further dehydrates slowly and leads to the formation of rust, that is Fe2O3.XH2O. Now how we can avoid the rusting? By doing paintings, by using alloying, that is adding the mixture of metal and non-metals, oiling, etc. Now acid. How will, if when iron reacts with any acid, we can take, here I am showing the example of hydrochloric acid, it can be sulfuric acid, it can be nitric acid, any other acid. So what happens if I'll take up iron powder in a test tube and add a hydrochloric acid and leads to the formation of bubbling of gas, which shows the hydrogen gas has been released and the salt formation will take place, which shows that it reacts with acid and leads to formation of that particular salt. Now complex formation, I had already taught you that what the basic of complex formation is. So magnetic properties. We all were fond of magnets when we were kids, that how they work, we have a great curiosity. The curiosity behind it was a chemistry, that is because of the ferromagnetic nature, because they all are unpaired. Iron is having unpaired electrons, due to which it has a magnetic moment and leads to attract the magnet, or we can say the metals. Now due to the versatile nature of iron, we used to say that it has a very versatile nature because it can easily switch from one oxidation state to another oxidation state, from +2 to 3, 3 to 2. So it has been used in Fenton reaction for the creation of OH radical. What happens when ferrous reacts with H2O2? It leads to the formation of ferric, and ferric further reacts with H2O2 and leads to formation of ferrous. Here again regeneration of ferrous has taken place and again we can form the ferric. which shows that iron is highly versatile. Now, what is the main mode of this reaction was? The generation of OH radical, which leads to break down the pollutants, dyes, or other insecticides, pesticides, etc. Now, there are various alloys of iron and the uses. Steel basically formed from iron plus carbon, stainless steel, iron plus chromium, cast iron, iron burned with a high content of carbon, wrought iron, pure iron with the slag, and alloys we usually use iron and other metals such as used in aircraft, tools, and heavy machinery. Now, how it has been used in our body? We are having an inbuilt iron in our hemoglobin in the form of ferrous. What happened? Each hemoglobin molecule has four porphyrin rings, and each porphyrin ring is having a 4 nitrogen atoms attached and one protein chain, and one side is vacant. And oxygen will come and bind to that state and leads to formation of a oxyhemoglobin. That means that our hemoglobin is binding towards the oxygen, and which helps to transfer the oxygen from lungs to the tissue, and again from tissues it will move to the further cell. Iron binds reversibly with oxygen, which shows that iron forms a bond with oxygen, but it doesn't form that strongly that it can't break the bond or it can't lose the oxygen easily. So it is very, we can say that versatile in this form also, that it can easily remove the oxygen and bind with the oxygen. Now, myoglobin is basically known as for the storage for oxygen for quick release. Whenever we go to gym or running or dancing, we need more oxygen because our energy is getting drained out. So at that moment, myoglobin helps to use that energy which is stored inside it, and also contain Fe2 positive in a heme group. These are the hemoglobin structure, 4 porphyrin rings, and here this one is the myoglobin image. Now, what is the role of it is already explained. Now, oxygen binding and release. What is cooperative binding? It tells us when the oxygen binds with the one porphyrin ring, the affinity for the other binding of oxygen will increase. This was explained by cooperative effect, and once that attached to second porphyrin ring, the other affinity will increase due to the changes in the globular chains of we can say the protein. So when the oxygen is attached to a hemoglobin, it is a relaxed form. When there is a decrease in oxygen, we can say that oxygen is not attaching to hemoglobin, it is in a tense form. Now, Bohr effect. Bohr effect basically deals with the pH. Now, in lungs are basically basic in nature. It always need, if in lungs we say hemoglobin attached to the oxygen, it always attaches to the oxygen in the basic condition. It will not attach with oxygen in the acidic condition. So, in lungs, the condition is it should be high pressure and high pH. That will lead to the binding of oxygen in the lungs. And if I'll talk about, for example, in why it doesn't why we need a myoglobin in the cells for the release of oxygen, because in cells we are having an acidic medium. How tissues react with oxygen leads to the formation of carbon dioxide, which is acidic in nature, and leads to decrease in the pH, and therefore their myoglobin will act, no hemoglobin will attach. Therefore that is the role of myoglobin, that it will help to release the oxygen into the cells. Now, okay, iron is present in hemoglobin and all. How iron is stored in our body? Who will transport the iron in our body? There are three main: ferritin, transferrin, and siderophores. Ferritin basically stores iron in ferric safely inside the cells, releases it when needed. Transferrin. Mostly we have iron in a ferrous form. It moves to the stomach, acidic condition, it converts into, it gets oxidized, it converts to a ferric. From there, transferrin will become active, it will transfer the ferric to ferritin for storage. Siderophores, these are iron containing complexes and transport the ferric, helps in transfer of ferric ions. Now, detection using the iron. One of the very important tests is Browning test, we all usually use in a graduation time. This test is not for the detection of iron, this is the test for the detection of nitrate, but here iron is used for the detection of nitrate. What happens, we take a test tube. For example, I am having a ligand, I want to check whether either it is having a nitrate or not. What I will do, I will take the compound, I'll add ferrous sulfate and H2SO4. What will happen? It will ferrous will convert into ferric, nitrate ion will convert into NO, and that NO will react with the remaining ferrous and leads to formation of this compound FeH2O5NO whole 2 positive. This will lead to formation of, what is the, how we'll come to know that this has formed? This will lead to formation of that brown color ring. This is the whole about brown ring test. From there we can come to know that yes, nitrate ions are present. This happened because of by the using of iron. So now this is all we came to know, that yes, iron is present and all. Now why the detection of iron is important? Why we want to detect iron in future? Why we are making so much chemosensors for the detection of iron? As excess or deficiency, both are bad. Deficiency in a body can cause anemia. Excess can cause liver diseases, heart problems, diabetes, etc. According to World Health Organization, it should be less than 0.3 ppm per day. Now, this creates the need for the accurate, selective and sensitive detection of ferrous and ferric ions. Now, the main question is, how can I detect iron? What are the easy methods? I don't want that much of labor work. I don't want to waste my time. I want cost effective. What are the main reasons by which what are the main instruments or we can use so it will be easy for me for the detection? So what should I do so I can easily detect the ferrous and ferric? The reason are UV and fluorescence. They are the main, we can say, instruments by which we can easily detect the other metal ions also. I am here giving the example of ferrous and ferric. Now why UV and fluorescence? These are simpler and less expensive. We can allow real-time analysis. Naked eye for simple optical sensors can detect in aqueous also. They are having a fast response. We shouldn't have to wait for a long time of period for 2 to 3 hours. They are so sudden. And the sensors can be functionalized with triazole, shift-based silanes, etc., tailored for copper 2 or iron, etc. Now here we are talking about shift bases, triazoles and silanes. Now what are shift bases? Shift bases are compounds containing an amine group or azomethane group formed by the condensation of amine with aldehyde. Contains lone pair at the nitrogen which can act as a donor atom. It has a various coordination, like nitrogen is having a lone pair, so it can easily give the electrons to the metal and can form a coordination bond. Can be designed to select it. We can make derivatives, or we can say we can design a shift base accordingly, then according to the need of our detection. So here it is written that shift base can be designed to selectively bind specific metals by modifying the functional groups or backbone. Some shift bases show they are having many properties like anti-cancer, antifungal, anti-inflammatory, etc. The one of the best part is that it is one pot synthesis under reflux or a room temperature, catalyst free, or a mild acid catalyst required sometimes, not every time. So what are the main properties why shift bases can act as a good chemosensors? The properties are presence of C double bond N, multidentate binding sites, tunable structure, conjugation and planarity, colorimetric and fluorescent behavior, strong chelation with ferrous or ferric or any other metal. Now here we are having a donor atom. Nitrogen will interact with the donor atom and form a coordination bond with the metal like ferrous and ferric. Now the properties, we are one by one explaining the property. Shift bases often contain additional donor atom OH-COH, enhancing the selectivity and stability of metal complexes. Each modification of ligand allows specific selectivity for specific metals like iron. And conjugation and planarity. Conjugation leads to the delocalization of electrons and inducing the UV visible and fluorescence response upon binding of the metal. Now, colorimetric and fluorescence behavior. Binding with metals causes shift in the absorbance. It can be any shift, increasing wavelength, decreasing batho, hypo, etc. And chelation, for the high affinity for metal ion enables selective detection even in the presence of other metal ions. Now, this was the work done in our lab by our seniors where the amine was reacted with aldehyde leads to formation of azodides. These are the particular conditions under which azodides are formed, and further reacted with alkyne leads to formation of azide, further formation of alkyne, and further reacted with azide to formation of organosilane. Now, UV visible. When we find that our ligand under the UV visible, on adding the iron, ferrous iron, there was a shifting of a peak from 371 to 358, and a new peak at 311 has been generated, which shows that there is some sort of, we can say that some sort of relation or interaction between the metal has been happened. Now, moving ahead, triazole. Hello. Yeah. Now triazole. Triazole is a heterocyclic organic compound that contains a 5 with 3 nitrogen atoms and the 2 carbon atoms. Here, when the triazole was formed, the 2 isomers were formed, that is 1,4 and 1,5. With we can say that 2 forms were forming, but as when in the use of copper, there was a proper that it leads to the formation of 1,5, which we mainly use in our labs. So this is the experiment performed in a lab where with aldehyde leads to the formation of here alkyne अच्छा इधर भी देख के करनी hello चल पड़ा so leads to the formation of Schiff bases and further reacted with azide and leads to the formation of organosilane, which was further then we further use the UV visible and fluorescence. In UV visible, we came to know that on the interaction of ferric ion, there was a shifting of peak from 325 to 290. That is a bathochromic shift, and in under fluorescence, it has been observed that on addition of ferric ion, there was a quenching in the absorption peak. So NMR was done and recorded, which shows that a main peak appeared at 8.83 and a peak at 0.5 also showed that the formation of complex has taken place. Now metal was further binded by the nitrogen of triazole and nitrogen of Schiff bases, which was further proved by NMR also. Now what are organosilanes? Organosilanes are basically a bond between carbon and silicon. They are widely used in the detection of metal ions like iron when combined with metal binding ligands like triazole, Schiff bases or other donor containing functional groups. Now this is the also experiment done in a lab where firstly alkyne was formed and further reacted by with amine of fluorine and leads to formation of Schiff base and further leads to formation of organosilane. Here we get the signal of on addition of iron into the ligand, we got a signal which a new peak has been appeared at 363. A new peak has been appeared at 363, which shows that there has some sort of interaction between the metal and the ligand. Now, okay, we come to know about the metal is showing different peak or at a different wavelength. Now, how I'll come to know that how much sensitive or how much minimum to minimum amount of ligand should be required for the sensing. So for that, titrations were performed. From titrations, we conclude the LOD, and the LOD came out to be 0.0723 into 10 raised to the minus 8 molar, which shows that it is highly, we can say that highly sensitive towards iron. Now selectivity. While performing the selectivity studies, that how much, even in the presence of other metal ions, how much our metal is selective or how much our ligand shows selectivity towards the only single metal. In here, anti-interference study proves that it is highly selective towards the ferrous ion. Now from NMR, proper shifting of the peak has been taken place from triazole moiety from 7.24 to 7.32, and the shifting of signal from 529 to 551 were also observed, which shows that or which proves the formation of compound with the metal complex. The iron was, ferric was bounded with the shift base of nitrogen, oxygen, and nitrogen of triazole. Now moving to the conclusion, iron is versatile. Ferrous and ferric oxidation states, enabling redox-based reactions. It forms stable coordination complexes with donor ligands, which is key sensor design. Chemosensors for iron detection has a high affinity for nitrogen, oxygen donors, change in color and fluorescence. Ligands like shift-based triazole and organocyllenes are widely used due to their selective binding, chromophoric or fluorophoric properties. These sensors allow for a rapid, sensitive, and selective detection of ferrous and ferric even in the mixed environment. So these are the publication of our lab under the supervision of Professor Gurjasprit Singh for ferrous and ferric. You can go through these publications. These are the highly sensitive chemosensors. There are many more also. I am showing few of them. So in the end, I would like to say iron is just not a metal, is a backbone of civilization, and it is built inside us. So it's play a major role whenever life or a chemistry goes, iron leads. Thank you so much.
Thank you, Ms. Pallavi. It was indeed a wonderful and insightful lecture. Now I would like to call Ms. Renuka for the next lecture. स्क्रीन पे मत देखना चलेगा उधर देख के
मैंने बैटरी चेंज नहीं किया, मैंने बोला था पक्का।
अब क्या बोल करना
अब इसमें बात कर सकते हैं।
Good afternoon, everyone. I am Renuka, and today I am standing here in front of you all to present a presentation that is based on the Leishmaniasis and the gold complexes used in the therapeutics of Leishmaniasis. So here is my title, that is the gold complexes in therapeutics, and how